Hello, my dear students. Welcome you all to Sri Jaindra Rank Zone classes. I'm your mentor and your friend for the subject chemistry, and I will be taking the organic chemistry. My dear students, following the previous videos in organic chemistry, we dealt about the general organic chemistry. We discussed about the IUPAC nomenclature. We discussed about types of bond cleavages, types of reaction intermediates, and in the last lecture, we started the inductive effect and the stability of carbon. Today, I am going to start with the stability of free radicals. So, let us start with the stability of free radicals. Free radicals, as you know, they are odd electron species. They are odd electron species, especially when we talk about the carbon. Okay. So, carbon as a free radical, the stability of free radical is directly proportional, directly dependent upon the presence of electron releasing groups. These electron releasing groups are basically the electron donating groups, okay? Or we can say the groups which shows the plus I positive inductive effect and inversely proportional to the groups having negative inductive effect, okay? When we talk about the tertiary free radical, secondary free radical, primary free radical, and methyl free radical. So which is more stable? Free radical mean carbon is having an unpaired electron, and if this carbon which is having an unpaired electron, if it attached to a carbon or to a group which can donate the electron to this carbon, okay, so it will get more stabilized. So tertiary, they are more stabilized than secondary, which are more stabilized than primary, which are more stabilized than methyl. Understood? Second example. All these are examples of free radicals. Here you can see the electron withdrawing group is directly attached to the carbon which is in a free radical state. It is more electronegative, it is less electronegative, it is least electronegative. And it is lastly the most electron donating group. So this is the electron releasing group. It will donate electrons. Okay. So this will be maximum stabilized here. So that it is mentioned that electron releasing group increases the stability, electron withdrawing groups decreases the stability. Okay. This example, when compared to which is more stabilized. Okay. See, this carbon which is having a free radical is attached to a carbon, and the carbon adjacent to this carbon is having an anode group. So it is electron withdrawing group. Okay. Here we have a meta position. This is para position, and this is ortho position. Okay. Here the NO2 will attract the electrons, and the resonance, or we can say not the resonance, the displacement of the electrons will require more of the area. Okay. So it is distance number power rule, that here the distance is increasing. Here the distance is maximum in para. Here in meta it is less in comparison to para. Here it is least. Okay. So the one which is having the least distance, okay, will be maximum stabilized. Then comes meta, and lastly para. Understood? Now comes stability of carbon. Stability of carbonyl, it is directly proportional to electron withdrawing group, or directly proportional to minus I group. This is tertiary carbonyl. Three alkyl groups will make the carbon more electron densile. It will decreases the stability of carbon to least stable. Then the primary, and then the methyl. So tertiary, secondary is more stable, primary is more stable than methyl. Understood? The CN will attract the electrons, and it will absorb the extra electron density over this carbon, making it more stable. Okay. This carbon is showing its own resonance, and as you know, resonance is more dominating effect than the inductive effect. So the COH and CN, when considered, when compared, so CN, the electron, the minus I effect of CN is, I should say, the minus I effect of CN is more in comparison to COH. Okay, CN is more electronegative than COH, and that is why the effect is more intense. Okay, so this is more stable than this compound, which is more stable than. Okay, so this is the stability of carbanion. Now, now we are going to talk about acidic strength. The acidic strength is measured by The position of equilibrium, that is position of ionization in water. Like Ha, it forms H plus A minus. The dissociation constant for this acid Ka is the concentration of the reactants upon the concentration of products upon the concentration of reactant. Okay, so K is the dissociation constant. The acidic strength is directly proportional to K and inversely proportional to pK, because pK is minus log Ka. Okay, acidic strength also depends upon the H plus ion concentration. Not only on this, that how much H plus ion is neutralizing the other compound. Okay, stability of acid anion. So these two things are which are measurable for the acidic strength. One is the concentration of H plus ions. Second, the stability of acid anion means conjugate base. Understood? So if the base or the conjugate base is more stable, then the acidic strength will be high. It is directly proportional to electron withdrawing group to minus I group. Okay, like HF, HCl, HBr, HI, which is more acidic. Whenever a question comes on the acidic character, what you have to do, you make the conjugate base, that is F minus. Now F minus, fluorine is more electronegative, I should say, most electronegative among the halogens. It is small in size. Okay, as the size is small, both fluorine and hydrogen, they can make a good bond, high bond dissociation enthalpy, and that is why the bond is not broken into H and F. Okay, understood? The correct order will be, because this is the bond order of decreasing bond strength, and decreasing bond strength means H can be easily released in the form of H plus. Okay, if we compare this, then the answer comes from electronegativity. The one which is more electronegative will attract the electrons, and the one which is more electronegative, okay, it will make the base, conjugate base, more strong. Okay, so HF will be then H2. Is that clear? Now comes the basic strength. Especially when we talk about the basicity of amines in gaseous phase. Okay, so basic strength is directly proportional to plus I effect. How? For example, this is ammonia having the lone pair. When we attach a methyl group, then the available electron density will be high because CH3 is electron releasing. So if CH3 is electron releasing, N will be acquiring more of electron density, more of negative charge, and it will easily accept the protons. Okay, so the proton accepting power is more in primary amine in comparison to ammonia. Then if we have two alkyl groups, then also same thing. Then tertiary alkyl group. Okay, is it clear? This is tertiary. So stability will be tertiary, then secondary, then primary, then methyl. Okay. So the basic strength increases the basic strength is directly proportional to 3 degree or the tertiary structures. The tertiary structure is more, then more will be the basic strength. Okay. Plus I power. Means alkyl amines like primary, secondary, and tertiary amines are more basic than normal amines. Okay. Now, the example can be Okay, like this is more basic than this. This compound is more basic because the lone pair is available. Okay, but the oxygen being more electronegative, it will attract the electrons and the lone pair availability will be lesser. So on the basis of basic strength in solvent phase amines, in case of air, it is primary, secondary, and tertiary. Means sorry, on the basis of air, so the basic strength will be 3 degree, 2 degree, 1 degree. On the basis of strength in solvent phase, RCH3, R2NH, RNH2, R3, स्टेबिलिटी बताइए इसकी, and ammonia. Okay, so on the basis of strength in solvent phase, the stability will be, it depends upon different factors. It depends upon different factors. So stability in solvent phase I will be discussing in the next turn. Till then, bye bye, take care, stay safe, stay healthy.